Okay, let's do a numerical example next where we find the capacitance in different ways. So first we have a capacitor which carries 120 picofarads. Pico is not one of those prefixes you're expected to remember. Pico means 10 to the minus 12. You are expected to catch that this is a prefix, which you can look up. So that's the charge on each plate. The potential difference is 10 volts. Please find the capacitance. So number one, charge 1 is 120 times 10 to the minus 12 coulombs. The potential difference delta V is 10 volts. We know that the capacitance C is charge over delta V. 120 times 10 to the minus 12 coulombs divided by 10 volts to get 12 times 10 to the minus 12 farads, or 12 picofarads. A picofarad is a quantity we frequently use when it comes to capacitances. Picofarads, nanofarads. Capacitances typically are very small. Okay, number two, we have a capacitor with square plates, and the side length of each plate is 50 millimeters. So for our second capacitor, L is 50 millimeters, so 50 times 10 to the minus 3 meters. The plates are separated by 1 millimeter, so the plate separation is 1 times 10 to the minus 3 meters. Find the capacitance of this one, so C2, let's see, we know the side length, we know the plate separation, and we know that capacitance is area times epsilon naught divided by the plate separation. Okay, this one's pretty straightforward. Area is going to be the length squared because the plates are square. Let's pop in our numbers. 50 times 10 to the minus 3 meters squared times epsilon naught 8.85. Oops, heck, I wrote an 8 instead of a 5. 8.85 times 10 to the minus 12 coulombs squared divided by newtons meters squared. And that's all divided by D2, 1 times 10 to the minus 3 meters. And we get this capacitance is 2.21 times 10 to the minus 11 farads, or 22.1 picofarads. Okay, last one. Last one's going to be a little bit trickier. For our last one, number 3, a capacitor has a potential difference of 150 volts. Delta V3, 150 volts, an electric field of 500,000 newtons per coulomb, remembering that that can also be volts per meter if we wish, because newtons per coulomb is the same as a volt per meter. The plates are circular, and the radius of the plates is 2.5 centimeters, 0.0250 meters. When we see that they're circular with the radius, that might cause us to remember that, oh yeah, I could find the area of those plates if I wish. Okay, let's see what we can do about this. We know that capacitance is Q over delta V. I do know my delta V, so maybe this is not a bad strategy to try, but if I wanted to use Q over delta V, I would have to figure out my Q. I wonder, is there a way I could use my electric field to find my Q? Okay, this is going to be my plan. So I'm going to try and find my Q. I know that my electric field is equal to sigma divided by epsilon naught. I know sigma is charge over area. And I know that the area of my circular plates is pi r squared. This looks kind of good. I can find my charge here. Q3 is equal to E3 times pi times R3 squared times epsilon naught. Pop my numbers in, 500,000 volts per meter times pi times 0.025 meters squared times epsilon naught. And we get our charge Q3 is 8.69 times 10 to the minus 9 coulombs. Now that I have my Q3, I can use my strategy Q over delta V. .69 times 10 to the minus 9 coulombs divided by 150 volts To get 5.79 times 10 to the minus 11 farads, you can leave it this way, or we can write it as 57.9 picofarads. Okay, so there's a numerical example calculating capacitances in different ways.